Chapter: Rotational Motion in Mechanics. 1. Angular displacement concept. Angular displacement is a measure of the angle through which a point or line has been rotated about a fixed axis. It is analogous to linear displacement in translational motion, but in the context of rotational motion. It is a vector quantity, indicating both the magnitude of the rotation and the direction of rotation, counterclockwise or clockwise. 1. Unit. Radians, rad. This is the standard unit used for angular displacement. 2. Formula. Theta equals SR, theta equals frac SR. Where theta is the angular displacement, in radians, SS is the arc length, in meters, RR is the radius of the circular path, in meters. In the case of a full rotation, the angular displacement is equal to 2 pi radians. Important notes. 1. A full revolution corresponds to 2 pi radians, so one complete rotation of an object around an axis corresponds to 2 pi radians, or 360 degrees. 2. Angular displacement is positive when the rotation is counterclockwise and negative when the rotation is clockwise, based on the right-hand rule. Example: if a point moves along a circular path of radius 1 meter and the point moves a distance of 3 meters along the arc, the angular displacement is theta equals SR equals 31 equals 3 radians, theta equals frac SR equals frac 1 equals 3 text radians. 2. Angular velocity concept. Angular velocity, omega, represents the rate of change of angular displacement with respect to time. It is the rotational analog of linear velocity and tells us how quickly an object is rotating. 1. Unit. Radians per second, radian per second. 2. Formula. Omega equals d theta dt, omega equals frac d theta dt. Where omega is the angular velocity, theta is the angular displacement, tt is the time. If the rotation is uniform, constant angular velocity, the formula simplifies to omega equals dth dt, omega equals frac delta t, where delta theta is the change in angular displacement, and delta t is the time interval. For circular motion, the angular velocity can be linked to linear velocity, vv, as v equals r dot operator omega v equals r, c dot omega, where rr is the radius of the circular path. Example: if a wheel completes 5 full rotations in 10 seconds, then the total angular displacement is theta equals 5 times 2 pi equals 10 pi radians, theta equals 5 times 2 pi equals 10 pi text radians. The angular velocity would be omega equals 10 pi 10 equals pi radian per second, omega equals frac 10 pi 10 equals pi text radian per second. 3. Angular acceleration concept. Angular acceleration, alpha, is the rate at which the angular velocity changes with respect to time. It is the rotational analog of linear acceleration. Angular acceleration occurs when the rate of rotation is changing, i.e., when an object is speeding up or slowing down rotationally. 1. Unit. Radians per second squared, radian per square second. 2. Formula. Alpha equals d omega dt, alpha equals frac d omega dt. Where alpha is the angular acceleration, omega is the angular velocity, tt is time. If angular velocity changes uniformly over time, then the angular acceleration is given by alpha equals dot t, alpha equals frac delta omega delta t. Example: if a wheel's angular velocity increases from 0 to 10 radians per second over 5 seconds, the angular acceleration is alpha equals 10 minus 0.5 equals 2 radians per square second, alpha equals frac 10.05 equals 2 text radian per second squared. 4. Relationship between linear and angular quantities. Rotational motion has a close relationship with linear motion, especially when considering the motion of a point on the edge of a rotating object. Linear velocity. The linear velocity of a point on the edge of a rotating object is related to the angular velocity by v equals r dot operator omega v equals r c dot omega, where 1. v is the linear velocity of a point on the object, meter per second. 2. r is the radius, m. 3. Omega is the angular velocity, radian per second. Linear acceleration. Similarly, the linear acceleration of a point on the object is related to the angular acceleration by a equals r dot operator alpha equals r c dot alpha, where 1. is the linear acceleration, meter per square second. 2. r is the radius, m. 3. Alpha is the angular acceleration, radian per square second. Example. If a rotating wheel has an angular velocity of 5 radians per second and a radius of 2 meters, the linear velocity at the edge of the wheel is v equals r dot operator omega equals 2 dot operator 5 equals 10 meters, sv equals r, c dot omega equals 2, c dot 5 equals 10, text, meter per second. 5. Torque, rotational force. Concept. Torque, tau, is the rotational equivalent of force. It measures the tendency of a force to cause an object to rotate around an axis. The torque depends on the magnitude of the force, the distance from the axis of rotation, and the angle at which the force is applied. 1. Unit. Newton meter, Nm. 2. Formula. Tau equals r dot operator f dot operator sin theta, tau equals r, c dot f, c dot sin theta, where tau is the torque, r is the distance from the axis of rotation to the point of application of the force, radius, ff is the applied force, theta is the angle between the position vector and the force vector. The net torque acting on an object causes it to have angular acceleration, and this relationship is governed by n area summation tau equals I dot operator alpha, sum, tau equals I, c dot alpha, where 1. N area summation tau, sum, tau is the net torque acting on the object. 2. Is the moment of inertia. 3. Alpha is the angular acceleration. Example. If a force of 10N is applied at a distance of 0.5 meters from the center of a wheel at a 90 degrees angle, the torque is tau equals r dot operator f dot operator sin 90 ring operator equals 0.5 dot operator 10 dot operator 1 equals 5n c dot pm, tau equals r c dot f c dot sin 90 caret circ equals 0.5, c dot 10, c dot 1 equals 5, text, nm. 6. Moment of inertia, rotational inertia, concept. The moment of inertia, 2, is the rotational analog of mass. It measures an object's resistance to changes in its rotational motion. It depends on the mass of the object and how that mass is distributed relative to the axis of rotation. 1. Unit. Kilogram meter squared, kilogram m squared. 2. Formula. I equals myriad 2 I equals sum m underscore ir underscore I squared, where 2 is the moment of inertia, mim underscore I is the mass of each particle, rir underscore I is the distance of each particle from the axis of rotation. Moment of inertia for common shapes. 1. Solid disk. About its center, I equals 12 Mr. 2 I equals, frac. 1, 2, mr squared. 2. Thin rod. About its center, I equals 112 milliliters 2 I equals, frac. 1, 12, ml squared. 3. Solid sphere. About its center, I equals 25 Mr. 2 I equals, frac. 2, 5, mr squared. Example. For a solid disk of mass 4 kilograms and radius 2 meters, the moment of inertia is I equals 12 Mr. 2 equals 12 times 4 times 22 equals 8 kilograms, c dot pm 2 I equals, frac. 1, 2, mr squared equals, frac. 1. 2 times 4 times 2 to the power of 2 equals 8, text, kilogram m squared. 7. Work, energy, and power in rotational motion. Work done by torque. The work done by a torque is the product of the torque and the angular displacement through which it acts. If the torque is constant, W equals tau. Operator theta W equals tau C dot theta, where 1. WW is the work done, joules. 2. Tau is the torque, Nm. 3. Theta is the angular displacement, radians. Rotational kinetic energy. The rotational kinetic energy, KE, of